Thanks, Randy. Good morning, everyone. It's a real pleasure to be here participating in an international conference again. I'd like to thank the organisers for the opportunity to talk to you today and also for putting together this really wonderful event and wonderful program. The experiments or the study I want to talk to you about today is really looking at quenches in Fermi gases and what we can learn about fermionic systems by performing quench experiments. So the experiments were done by my team at Swinburne, and we've had some very productive and helpful collaborations with some theorists who are spread across Europe. And I'll just mention that both Alan and Denise are in the audience here as well, so great to see some people in person again. Okay, an outline of what I'll talk to you about. There's essentially two quench scenarios that I want to consider. The first is quenching a gas from the normal phase, or using a sudden change in the interactions to quench from the normal phase into the superfluid phase, and what we can learn about pair formation, pair condensation, and even the contact in these systems as they approach equilibrium. And also, the second scenario will be about quenches within the superfluid phase and how these can be used to study the Higgs amplitude mode. Okay, we've already heard quite a bit about non-equilibrium and dynamical experiments using cold atoms in this conference. So we had very nice talks already, including Isabelle Bouchul's talk yesterday on generalised hydrodynamics. And really, one of the ways I like to think about this is that cold atoms give us a very nice way to experimentally explore the different, or the dynamics of the different correlations spanning the vastly different spatio-temporal scales that can play a prominent role in setting the dynamics of systems out of equilibrium. Now, I've listed here a range of various studies, but there's, of course, this is only a selection, and apologies for leaving out any relevant papers here, but just to give a feel that this is a very active area. Okay, the system that we're going to use in our studies is something of a, I guess by nowadays, a vanilla flavoured or old-fashioned Fermi gas experiment, so just a three-dimensional Fermi gas of lithium-6 atoms, where we have an equal number of spin-up, spin-down particles in the system, and we can control the S-wave interactions between these two spin states using the Broad-Feshbach resonance. And this gives rise, so even these very simple ingredients give rise to this quite rich phase diagram of the BCS to BEC crossover with this resonantly interacting region in the middle. The way we produce these systems in the lab is using a combined, or we evaporatively cool clouds in a combined optical and magnetic trap. So we use two parallel light sheets to confine the atoms in the vertical plane, and then a harmonic potential in the radial, in the two radial directions produced by magnetic field curvature. And so it means we end up with oblate-shaped clouds that we can kind of tune between a kind of pancake shape to a more English muffin shaped cloud. Okay, so that's the system that we're going to be using. Let's now have a look at the first quench that I want to talk about. So the idea is here that we're going to start somewhere over here on the phase diagram. So that is in the quite a way towards the BCS regime, where we have a fairly good handle on the parameters through perturbative theories and Li-Huang-Yang terms, etc. And then suddenly, or ramp the interactions from this point to unitarity at a range of speeds, and have a look at the subsequent dynamics and what we can learn from that. So the nice thing about this is that with interaction quenches, we can cross this transition, provided we don't heat up too much. We can cross this transition on timescales shorter than have previously been investigated. So this picture here shows the experimental sequence. We ramp in a time tq, we hold for some time, and then we can take an image either using the rapid ramp technique, so where we turn off the optical trap, project onto deeply bound molecules, let those molecules expand for some time, and then dissociate them again and take a picture, and that allows us access to the pair momentum distribution. Or we can simply take an in situ image of the cloud in the trap, so at this point here. So if we do the in situ image, you can see that actually, or you can barely see any changes happening there, so there doesn't look like there's much happening in the bulk system. But then when we do the rapid ramp and the looking at the pair momentum distribution, you can see that it starts off, if you catch it just at the very short times here, it starts off as a broad distribution, but very quickly we see the appearance of this bright peak in the middle, and then eventually, after long times, the formation of a nice clear bimodal distribution, indicating the presence of a pair condensate. Okay, so how can we analyse these images a little more quantitatively? Well, what we can do is integrate those 2D profiles over one dimension. We find that the wings of these integrated profiles are described very well by a Gaussian, so we just fit the wings of all these different distributions, or the region outside these dashed lines, with the Gaussian. At very short times after the quench, the Gaussian actually continues to fit the central part of the cloud. But then as the whole time goes on and on, we see that on top of this Gaussian peak, we get a kind of additional bump in the middle. And so this corresponds to additional particles appearing in low momentum modes, which we interpret as being the production of pairs, or pairs forming in low momentum states. So you can see that the area of this, so the shaded area here on top of the Gaussian, I'll refer to that as the non-Gaussian fraction, that appears relatively quickly, and then grows up, and eventually, after a long hold time, takes the shape of a nice sharp molecular condensate. So we can look at a couple of properties from this. So if we measure the area of this portion on top of the Gaussian, that really tells us about the time evolution of the number of pairs in the system. And so we see that, so for the shortest quench, for example, this 50 microsecond quench, the yellow points here, you can see that between 100 microseconds and 200 microseconds, there's a huge jump. We go from basically nothing to having quite a reasonable fraction of pairs, and then it changes a little bit, but most of the dynamics happens very quickly here. So what this is telling us is that the pair formation in this cloud after we do the quench is happening on a timescale of 100 microseconds or so, and this is, we can compare this to the Fermi time in the system. So in the centre of the trap, the Fermi time's around 26 microseconds. So what we can see here is that the pair formation appears to be governed by the local properties of the system. So the local Fermi energy is setting the scale for that. However, in addition to the formation of the pairs, there's also the dynamics of these pairs as they approach equilibrium. And the way we can see that is we can look at the shape of these non-Gaussian peaks. So this now shows you the distributions with the Gaussian part subtracted away, and you can see that the shape goes from something quite flat to something a little bit more peaked. Then eventually, after around 100 milliseconds, we get a sharply defined condensate peak. And so this tells us actually that despite the fact that pairs can form very quickly, the dynamics in the low momentum modes that are associated with the production of a pair condensate take place over much longer timescales, so up to 100 milliseconds or so, or 3 orders of magnitude longer roughly, for these more non-adiabatic quenches. So we can see these things happening on quite different timescales. We can also use measurements of the potential energy of the cloud after it's come to equilibrium following the quench to learn about the contact. We can measure the temperature to learn about the adiabaticity, but I won't go into the details here, but using a combination of tan relations, so the adiabatic and virial relations, we can relate the changes in potential energy from the quench to the evolution of the contact. And what we find is that the only way we can understand these results is if the contact already changes quite significantly during even the very shortest quenches here. So contact, on the other hand, refers to extremely short-range correlations. So it's perhaps not surprising that these should happen on very short timescales, but this is now verified in these experiments. Okay, so that's what we can learn by quenching from, or there's some of the things we can learn by quenching from the normal to the superfluid phase. And that hopefully sets the scene for the next part of the talk, which is going to be concerned with quenches within the superfluid phase that excite the Higgs mode. Okay, so just as by way of reminder, this slide here, I'm going to go through the general picture that we have, or that people usually use for describing the Higgs mode. So when we have a system that undergoes, that undergoes a phase transition, which spontaneously breaks some sort of continuous symmetry, then particularly if we go to an ordered phase or a symmetry broken state where we've got that can be described by a wave function with an amplitude and a phase term, this typically leads to the appearance of two types of collective excitations. One to do with fluctuations of the phase, so that's picking a different point around this circle here. So all of these points at the bottom of the circle are degenerate in energy, so that is, the energy of the system can't depend on the phase of the macroscopic wave function. And so that leads to, in neutral systems, this leads to a gapless phonon mode, or the Nambu-Goldstone mode. But in addition to that, we can get situations where the orthogonal excitation, so in the amplitude, we can get a stable collective oscillation, a collective mode as well, which is referred to as the amplitude mode, so fluctuations in the amplitude of the order parameter. And this is the Higgs mode. And so these types of collective excitations appear in a number of settings. They've been studied for many decades, in fact, now in condensed matter systems. So things like charge density waves, superconductors, even liquid helium-3. And also there's the obvious connection to elementary particle physics and the Higgs boson there. So this is the kind of picture. Well, I'll also mention that in superconductors, this Goldstone mode gets pushed up to the plasma frequency because of the charge of the electron. So in addition to these studies, Higgs excitations have been studied already in cold atom systems. So some very nice experiments from Klaus Sengstock's group and also Emmanuel Bloch's group looking at Higgs excitations in Bose gases in optical lattices near the superfluid Mott insulator transition, and also in a supersolid-like phase in Tillman-Esslinger's group, where the Bose gas was confined in two optical cavities. And more recently, we heard in Francesca's talk and also related work from Tillman Vale and Giovanni Madugno's group, that Higgs excitations and these sorts of collective excitations are can appear in dipole supersolid gases. In addition to this, there's some experiments from Michael Curl's group in Bonn where they observed the Higgs excitation in strongly interacting Fermi gases. And so this, I guess, begs the question, well, why am I here talking to you about it? Well, actually, what I want to say about that is that essentially all of these studies, or the majority of these studies, have used spectroscopic probes whereby the system has been driven at the frequency where the Higgs mode is expected, and seen that the system actually responds at that particular frequency to identify the Higgs mode. What we are trying to do in our experiments is actually to observe the oscillations of the order parameter more directly, and in so doing, get access to a few additional properties in the system. Okay, so the way we're going to tackle this in our experiments is we're going to use a quench again. This time we're going to start somewhere quite close to unitarity, so already below the superfluid transition, and then jump just straight back to unitarity. Okay, so a conceptual, or perhaps a conceptual way to picture what or to think about what we're doing here is we're starting off with a system in equilibrium. We might have some superfluid pairs already present, as well as some unpaired normal fermions. When we jump the interactions here, what we're doing is we're really taking this state and projecting it onto a new set of basis states, if you like. So the two, or the paired state, so the gap increases when we jump this way across in the interactions. So we're projecting onto a more tightly bound pairs, or a deeper, larger pairing gap. And so that, and then in addition to that, there might be also some superposition of excited states that are mixed in. So if we think about the ground state being here and then the excited states being up here, we're projecting this, this initial state onto these new states, making a superposition of that, and that superposition, of course, will oscillate at a frequency given by the energy difference between those states. So depending on the dispersion of the single particle states in the excited states, depending on the wave vector of the particles involved in the pairing, the dispersion means that they might all be excited with slightly different energies, or we could excite them to different points in the continuum. So initially, the oscillations, or we can think about this somehow as oscillations in the pairing size, initially they'll start off all in phase with each other, but because of the slightly different excited state energies, after some time these oscillations will dephase and will lead to a damping in the oscillations of the order parameter. So this is these are the sort of features we're hoping to see in the experiment. Okay, so the first approach we could try would be to say, well, we've seen that we can do the rapid ramp measurements, and that tells us about the condensate fraction. However, when we do the rapid ramp fraction, or the rapid ramp experiments, we're really integrating over the whole density distribution in the cloud. So these are harmonically trapped clouds. So the density changes with position, which means the Fermi energy changes. And so at unitarity, where it's the Fermi energy that really sets the pairing gap, we expect this to be different across the cloud. And so when we integrate over all of that, the oscillations damp out quite quickly. And this is shown, or well, seen in our early experiments, but also backed up by some theoretical calculations using LDA from our theory collaborators here. So then we thought, well, actually we know how to probe a more localized region in the cloud, and we can do that using Bragg scattering, using a two-photon Bragg transition. So what we do is What we do is we take two laser beams, tightly focus them so that they intersect in the center of our atom cloud, where the density is quite homogeneous, and we tune the Bragg frequency to be exactly half the atomic recoil frequency, or h bar squared k squared on 4m. And the idea with that is that it would, in a single particle picture, we would be directly addressing particles with mass 2m and zero momentum. And so if we measure the Bragg response then as a function of the condensate fraction, we can see that the Bragg response is very sensitive to the condensate fraction at this frequency. So we can detect condensate fraction, but we should be a little bit careful here as well. So actually what we really need to think about is that actually measuring the gap or the amplitude of the order parameter. And so perhaps a more rigorous way to think about this is that when we do a Bragg spectroscopy experiment, we're really measuring the imaginary part of the density-density response function, which for a strongly interacting Fermi gas looks something like this. So we've got this, basically this threshold energy here, which is connected to the pair breaking energy. And this happens to be very close to the half the atomic recoil frequency, or the pair scattering frequency. And so what we expect is actually that if we have some oscillations in the order parameter, that this excitation spectrum should shift back and forth a little bit. So the arrow here is really meant to indicate the shifts of this excitation spectrum. So we can think of our experiment then when we park our Bragg frequency here, so that there's some finite spectral widths of the Bragg pulse. But when we park our Bragg frequency here, as this response function oscillates back and forth, because there's some gradient here, we expect to detect a change in the Bragg signal that we measure. And so this is what we're going to look for. All right. So the way we do these experiments then, we just use a short quench, so 50 microsecond quench from a little bit on the BCS side back to unitarity. Probe with the Bragg lasers, we see we kick the atoms quite strong, so we end up with a large signal. We take the difference of this signal between an un-Bragg scattered cloud, and we work out the centre of mass displacement, that the subsequent centre of mass displacement. And as you can see, if we look at this Bragg signal, it does show these damped oscillations that we were hoping to see. So this quite clearly shows the Higgs mode in the Fermi gas, and we can now fit these sorts of traces with a damped sinusoidal function, so with some amplitude, a phase that actually we're not too worried about, but we've also got a frequency and a decay coefficient. So the amplitude oscillations are expected to decay with a power law dependence, so t to the some power gamma here. And we can now use these measurements to investigate all these parameters. So to give you an idea what we see, if we change the temperature of the cloud when we excite the Higgs mode, we find that the Higgs oscillations are quite strongly temperature dependent, so they're much more visible in colder clouds than in hotter clouds. And by the time we've got to the transition temperature, we really don't see any evidence of oscillations at all. We can compare the measured amplitudes, so this is really just that, sorry if I go back here, just these parameters A, the amplitude of the oscillation, divided by the offset, or the kind of asymptotic response, the asymptotic Bragg response. We can compare that to theoretical calculations, and we see that indeed the amplitude does increase quickly with decreasing temperature as expected from the theory. And this theory is really, there's no free parameters in this theory, so this is really comparing a normalised theory with normalised experiments. And I should also mention that the TC, this is T on TC here, this is the critical temperature actually before the quench. So if we quench from above TC in the BCS phase, we don't detect any oscillations either. So the amplitude of the oscillations really goes to zero as the initial temperature approaches the critical temperature. So in addition to the amplitude, we can look at the frequency of the Higgs oscillations, and what we find is actually quite striking, that over the relatively small temperature range that we've probed, the frequency of these oscillations stays fairly constant. So in the limit that where I guess strictly speaking, it's the limit where we have a very small quench, the frequency of the Higgs mode should provide a measure of the gap. And so in our systems, we find something roughly around 0.42 or 0.43 as the fitted oscillation frequency. This agrees quite well with earlier measurements of the gap based on RF spectroscopy at MIT, and also Bragg experiments in our group, and also in Henning-Moritz group in Hamburg. And so this is, okay, thanks. So the frequency, or the frequency seems relatively stable with temperature. And we can also look at the decay coefficients. So we find, or the decay exponent, so we find that actually our data, it's quite noisy still, but sits pretty much right in the middle between the BCS and the BEC expectations. So these results for the BCS and the BEC limits are rigorous results. The first was shown roughly 50 years ago for the case of a BCS superconductor, and Victor Gurari showed back in 2009 that the BEC limit, these should decay as or the decay exponent should be 3/2. Okay, I'll just quickly flash up a couple of slides that we've also started to look at the interaction dependence here, and we see that the Higgs oscillation frequency changes quite dramatically. This we can use to map out the gap, or the pairing gap, as a function of interactions. And also we have some preliminary indications that as we go onto the BCS side, the decay exponent seems to approach more like the BCS expectation value. So I'll finish up there, but just say that we've used these quenches to learn about formation of superfluid and study Higgs oscillations, or the Higgs mode in a Fermi superfluid. We're still looking at various effects with our theory collaborators. So, for example, how the finite volume of the Bragg probed region can affect the damping rates that we measure. But with that, I'd like to thank you all for your attention, and also thank my team shown here at Swinburne. Thank you.
Thank you, Chris, for that very nice talk. We have plenty of time for questions. Bill.
Okay, now, because I got a lot of questions. I'm sorry.
I've still got time to run.
Yeah. Okay. Right. So it's for the first part of the talk where you were doing the quench from normal to superfluid. Okay. Now there were two time scales that were separated by a lot. So you did so this is where you do a quick quench. It's like a 50 microsecond quench, and then within 100 microseconds, if I've understood correctly, you were seeing the formation of the non-Gaussian part.
Yes.
But then it took a really long time.
Yeah.
Again, I want to make sure I've understood correctly.
Yeah,
then it takes a really long time for that non-Gaussian part to narrow up. Have I got
Correct.
that right?
Yes, exactly.
Okay, great.
Yeah.
Now, what you told us was that the fast formation of the non-Gaussian part was essentially the Fermi energy.
So it was pairs forming, so we interpret that as pairs forming on the time scale of the Fermi energy.
Fermi energy,
yeah.
right. Yeah. And then, okay, so the question is, why is that the right time scale? And then what is the physical right time scale that corresponds to the long time that it takes to form the, well, I guess you could say form the condensate or narrow up the velocity distribution?
Yeah, very good questions. So I think, so to address the first part, it's essentially saying that somehow we can consider the gases in this sort of local density approximation picture that we often use with these strongly interacting Fermi gases, that locally we can consider the properties of the gas as being set by just imagining it's a system with some density, some average density that's basically not changing much in this volume. And within that volume, we can treat it as some sort of homogeneous system, but then it's really the only energy scale that enters that system is the Fermi energy. And we know that the Fermi energy sets the binding energy, or the pairing gap, at unitarity. So that's really the only energy scale that we expect to enter there. I don't know, is that kind of along the answering your question or not?
Sort of, except it just feels like a cop-out, because I've heard this story about it's the only energy scale so many times, when it turns out that, well, if you think about it long enough, there's other energy scales as well. But so I don't know, I guess I'd be more satisfied if you gave me a little bit more of how the pairs form and why the Fermi energy is the thing that determines that.
That is a good question. I'm probably going to stick to my cop-out answer. But so the density. So when I say the Fermi energy, that's set by the density prior to the quench.
Yeah.
So the density hasn't had a chance to sort of rearrange itself. Yeah. So there is just whatever density we have before the quench, and yeah, I'm going to stick to my
Okay.
cop-out answer. Sorry, I can't do much better than that. Yeah.
Okay, but what about the second one? So why does it take so long after having formed some pairs to have those pairs create? I mean, it's not like this question hasn't been asked.
Yeah, okay, but you're
Before.
still asking it, so
Yeah.
I don't feel too bad for not having a good answer. So that is a good question. I think the other timescale that we can think about is the harmonic trapping timescale. So if we take the 1 over the geometric mean trapping scale for these experiments, that's around 3 milliseconds, which is actually very short compared to this timescale. So I think what the way we interpret that is that we're actually producing some long wavelength excitations in the system when we do the quench, and those long wavelength excitations are taking some time to settle down, like up to 100 milliseconds or so.
And settle down means what, dissipate some energy to the thermal cloud, or?
Yeah, I think so, yeah. So I think there's still exchange between the pairs and the thermal cloud. So the thermal distribution is probably not yet in equilibrium either, because these two things are very much in thermal contact. So yes, and I think this is... So it's a really good question, and I think would be interesting perhaps to try and address this would be to change this time scale a little bit and see how that affects this time scale, which is something we haven't done, but would be very interesting to look at. Yeah.
So I have a question, Chris. So how does this 0.17 for TC compare to other measurements? How is your uncertainty in comparison?
Yeah, that's a good question as well. Let me go ahead to that. So actually, we do the thermometry by fitting the equation of state to measurements of the in situ density here. So that's how we determine this temperature. But I should emphasize that we also wait for the cloud, for any dynamics to settle down. So we measure this temperature after, almost a second hold time in the trap. So we really make sure there's no dynamics happening that we can see. So this is, within our error bar, I haven't included an error bar on our temperature measurements here, but it's typically about 0.01 or between 0.01 and 0.02 is our best guess at the uncertainty in that, and that's usually based on the uncertainty in how well we can measure the density, not the uncertainty that comes from the fit, but just how well we trust our absorption images. Yeah. But with this one, I want to say that the oscillations, these Higgs oscillations, seem to disappear by the time we get to an initial, or if we measure the temperature after the quench, when that's around 0.15 or 0.16 of the Fermi temperature. So even it's below TC at unitarity, but it wasn't below TC before the quench, then we don't see any Higgs oscillation. So we really have to be able to do, and we check this using rapid ramp. So we really have to, when we use a rapid ramp experiment on the cloud to look for a condensate fraction before the quench, when we have that, that's when we see the Higgs oscillation. When we don't have that, we don't detect the Higgs oscillation, or it's below our measurement sensitivity.
Okay. So any other questions? If not, let's thank Chris again.